Welcome back. I am back with a new topic, that is calorimetry. Isolated system. If no exchange or transfer of heat occurs between the system and its surrounding, then the system is called isolated system. Calorimeter. It consists of a metallic vessel and a stirrer of the same material like copper or aluminum. The vessel is kept inside a wooden jacket which contains heat insulated material like glass, wood, cotton, etc. The outer jacket acts as a heat shield and reduces the heat loss from the inner vessel. There is an opening in the outer jacket through which a mercury thermometer can be inserted into the calorimeter. The figure of calorimeter is shown in the figure. Principle of calorimetry. When a body at higher temperature is brought in contact with another body at lower temperature, the heat lost by the heat lost by the hot body is equal to the heat gained by the colder body, provided no heat is allowed to escape to the surroundings. Thus, heat lost equals to heat gain. This is the principle of calorimetry. Example: a sphere of aluminum of 0.47 kg placed for sufficient time in a vessel containing boiling water so that the sphere is at 100 degrees Celsius. It is then immediately transferred to 0.14 kg copper calorimeter containing 0.25 kg of water at 20 degrees Celsius. The temperature of water rises and attained a steady state at 23 degrees Celsius. Calculate the specific heat capacity of aluminum. Solution: let the common temperature be T degrees Celsius. Now, from the principle of calorimetry, we know that heat lost by a sphere must be the heat gained by calorimetry, or minus dq sphere equals to dq calorimetry plus dq water. Equals to, this implies minus m aluminum s aluminum under bracket tf minus ti equals to m copper s copper into Tf minus Ti plus m water S water into Tf minus Ti. Now putting all value which is given, we get, and solving, we get a specific heat of aluminum equals to 0.91911 into 10 to the power 3 kilojoule per kg per Kelvin. Next example: when a 0.15 kg of ice of 0 degrees Celsius mixed with 0.3 kg of water at 50 degrees Celsius in a container, the resulting temperature is 6.7 degrees Celsius. Calculate the heat of fusion of ice. The specific heat of water is given 4186 joule per kg per Kelvin. This is very simple problem. You can use directly calorimetric principle, that is, heat lost by water must be equal to the heat gain to the melt the ice plus heat gain to the raise the temperature of ice water. This implies minus mw sw delta t equals to m ice lf plus m ice into sw into delta t dash. Using all value, that is mw mass of water equals to 0.15 and sw a specific heat of water 4186 and temperature difference 66.7 minus 50 equals to 0.15 into lv into 0.15 into 4186 into 6.7 minus 0, and so we have this imply 54,376.14 equals to 0.15 LV plus 4,206.93, and from this we get LF, that is latent heat of fusion, equals to 3.34 into 10 to the power 5 joule per kg. Next example, calculate the heat required to convert 3 kg of ice at minus 16 degrees Celsius kept in a calorimeter to estimate 100 degrees Celsius at atmospheric pressure, given a specific heat capacity of ice 2100 joule per kg per Kelvin, specific heat capacity of water 4186 joule per kg per Kelvin, and latent heat of fusion of ice equals to 3.35 into 10 to the power 5 joule per kg, and latent of heat steam equals to 2.256 into 10 to the power 6 joule per kg. This problem also can be solved by the principle of calorimetry. Here the situation, here different value is given, that is mass of ice is 3 kg, specific heat of ice is 2100 joule per kg per Kelvin, specific heat of water 4186 joule per kg per Kelvin, latent heat of ice equal to 3.35 into 10 to the power 5 joule per kg, and latent heat of steam is 2.256 into 10 to the power 6 joule per kg. Now here the situation for solving is shown in the figure. Let 3 kg of ice at 22 degrees Celsius transfers to the 3 kg of ice at 0 degrees Celsius, and this takes the heat Q1. Now this ice will convert into 3 kg of water, and at this point Q2 heat is added. Again 3 kg of water is at 0 degrees Celsius go to 3 kg of water 100 degrees Celsius, and in this process Q3 heat is taken. Again from water at 100 degrees Celsius convert into 3 kg of steam at 100 degrees Celsius, and this process is done with addition of Q4 heat. So we have now Q1 is equal to heat required to bring the ice from minus 12 degrees Celsius to 0 degrees Celsius, m ice into s ice into dt equals to 3 into 2100 into under bracket 0 minus of 12 equals to 36 into 2100 joule. Second, Q2, heat required to convert ice at 0 degrees Celsius to water at 0 degrees Celsius. The m ice into L ice equals to 3 into 3.35 into 10 to the power 5 joule. Q3, heat required to bring water at 0 degrees Celsius to water at 100 degrees Celsius. MWSW into dt, 3 into 4186 into 100 minus 0. And Q4, heat required to convert water at 100 degrees Celsius to steam at 100 degrees Celsius. MW into L steam equals to 3 into 2.256 into 10 to the power 6 joule. Hence total heat required Q equals to Q1 plus Q2 plus Q3 plus Q4. Putting these values, we finally get Q equals to 9.1 into 10 to the power 6 joule. Answer. Now heat transfer. Our next topic is heat transfer. There are three modes of heat transfer: conduction, convection and radiation. Let's start with the conduction. It is the mechanism of transfer of heat between two adjacent parts of a body because of their temperature difference. In this process, heat energy is transferred due to oscillation of molecules of the material without movement of molecules from one position to another position. Consider a rod is heated by furnace, and we see in the figure that every point different point of rod is at different temperature, that is T1, T2, T3, T4, T5, T6 and dash. Now because heat is given at T1 point, so T1 must be greater than T2 and must be greater than T3, must be greater than T5, so on. Now a steady state. When the temperature of the body at every point becomes constant, then it is said to be in a steady state. It is found experimentally that in the steady state, the rate of flow of heat or heat current H is directly proportional to the temperature difference and area of cross section and inversely proportional to the length between the ends. As shown in the figure, a rod of length L with cross sectional area A and with temperature T2 and T1 at the ends are shown. Now from above principle, we know that heat current is directly proportional to the temperature difference between the ends, that is H proportional to T2 minus T1, H proportional to A, that is cross section of area, and H proportional to 1 by L, that is length, inversely proportional to length. So we have H proportional to A into under bracket T2 minus T1 by L, where T2 is the higher temperature where T2 is the temperature of end with higher temperature and T1 is the end with lower temperature, and L is the length of rod and A is the cross sectional area of A. Hence H equals to Ka into T2 minus T1 by L, where K is a proportionality constant called thermal conductivity of the material. Here H equals to dq by dt, heat current or heat flown per unit time. A is the area of cross section of the rod, L is the length of the rod, T2 minus T1 is the temperature difference between the ends. The constant of proportionality K is called thermal conductivity of the material, and its SI unit is joule per second into meter by meter square into Kelvin, equals to joule per second per meter per Kelvin or watt per meter per Kelvin, because joule per second is watt. Example: what is the temperature of the steel copper junction in the steady state of the system shown in the figure here, in which given length of a steel equals to 15.0 cm, length of copper equals to 10.0 centimeter, area of cross section of a steel bar is 2 times the area of cross section of copper bar, and thermal conductivity of a steel is 15.2 into 15.2 joule per second per meter per Kelvin, and thermal conductivity of copper is 385 joule per second per meter per Kelvin. Solution: let the common temperature is T. In a steady state, incoming heat current at junction must be equal to outgoing heat current at same junction. This implies K1A1 into T2 minus T by L1 equals to K2A2 T minus 0 by L2. This implies K1 A1 by L1 into T2 minus K1 A1 by L1 into T equals to K2 A2 by L2 into T. This implies K1 A1 T2 by L1 equals to K1 A1 by L1 plus K2 A2 by L2 into T. And this implies T equals to K1 A1 T2 by L1 divided by K1 A1 by L1 plus K2 A2 by L2. And solving this, finally we get T equals to 2 K1 L1 T2 divided by 2 K1 L2 plus L1 K2. Using all the given value, we get 44.4 degrees Celsius answer. Example. Here two bar is connected at a junction. The junction temperature is T0 and one end is at T2 and the other end is at T1. One rod length is L2 and the other rod length is L1. Then we have to find the temperature T0. Here we can use same principle, S2 equals to H1, that is heat current at T0, incoming heat at T0 at incoming heat at junction must be equal to outgoing heat at junction. This implies K2 A2 into T2 minus T0 by L2 equals to K1 H1 K1 A1 into T0 minus T1 by L1. Now solving this, finally we get T0 equals to or T0 equals to K1 A1 T1 by L1 plus K2 A2 T2 by L2 divided by K1 A1 by L1 plus K2 A2 by L2. Now different cases can be made for this formula. Case A, if cross-sectional area is same for both rod, then A1 equals to A2 equals to A. Say the situational figure is shown in the figure. Now from above formula, T0 will be equal to K1 T1 by L1 plus K2 T2 by L2 divided by K1 by L1 plus K2 by L2. Solving, we get K1 L2 into T1 plus K2 T2 into L1 divided by K1 L2 plus K2 L1. Case 2. If cross-sectional area is same and also length is also same, then using this condition in above formula, we get T0 equals to K1 T1 by L plus K2 T2 by L divided by K1 by L plus K2 by L. Solving it, we get T0 equals to K1 T1 plus K2 T2 by K1 plus K2. And in this case, heat current H equals to K2A into T2 minus T0 by L equals to K1A into T0 minus T1 by L, or H equals to K2A by L into under bracket T2 minus K1 T1 plus K2 T2 by K1 plus K2. Solving, we get H equals to K1 K2 into A into under bracket T2 minus T1 divided by under bracket K1 plus K2 into L. And for it, heat current H dash equals to K dash into A into T2 minus T1 by 2L. Heat current should be same in both cases, hence H equals to H dash. And solving this, we get K dash equals to 2K1 into K2 by K1 plus K2 equivalent to conductivity. Convection, it is the mode of heat transfer by actual motion of matter. It is possible only in fluid. Question, write notes on sea bridge and land bridge 3 trade wind. Radiation, it is the process of heat transfer from one point to another without intervening medium. The energy is transferred due to electromagnetic wave which travels with a speed of 3 into 10 to the power 8 meter per second in vacuum.